All right, hello everyone. We're talking today about what is probably the biggest idea in stats as we do statistics. It's the one that comes up the most often, and that is the normal distribution. Now, so far, we've talked about distributions, and when I say distribution, there should be a definition that pops into your head now. You think, okay, it's how often the variable takes on certain values, right? What values the variable takes on, how often it takes on those values. And distributions can have certain shapes. We've talked about symmetric or skew. One particular shape that seems to come up a lot is the normal distribution. Now, the normal distribution looks like this. It's just kind of this hill shape. Big peak at the center, it's symmetric, it goes off to the tails at the side. Lots of things in nature appear to be normally distributed. If you've ever gone to the gym, you might have noticed if you look at like you're doing that lateral pull down exercise, right? You grab the bar and you pull it down over and over, and there's those rectangular bars. If you've never been to the gym, sorry, but if you've been to the gym, there's these like skinny rectangular weights, and then there's a little peg, and you pull the pin out, and you put the pin in a certain hole, and then it lifts up so many plates. If the gym equipment is old enough, over time, many people using that equipment has kind of worn around the holes in the plates, right? So the pin going in and out over and over and over for a long time starts to wear around the holes. And if you look at it, you can kind of see a normal distribution. If you Google this, you'll normal distribution example weights or whatever, you'll see that for the average weight that most people lift or pull, you'll see a more marked wear. And as we move away in this rough shape of decreasing as we get away from the mean, there's less wear. And at the very extreme ends, one plate or all the plates, there might not be any wear at all because most people don't do only one plate or all of the plates. So very few people. So this shape, this normal distribution, where most of the things are clustered near the mean, which is at this single peak here, and then very little of it is away, is so useful. It comes up so often that we use it a lot. And I didn't do a very good job of drawing the curve. I'll try to do a better job. There we go. I think that might be a little bit more legible. We have the mean mu, and at the inflection point here, where the curve stops bending down and it starts bending up, it's flattening out, like around here, this distance would be one standard deviation, one sigma, and to the other side as well. So this is plus sigma and minus sigma here. And we'll come back to that in a minute. But a normal curve is entirely determined by its mean and its standard deviation. So sometimes we write this notation. We write n, and then we'll have mu and sigma. So some distribution, some variable x will be approximately normal. Oh, I didn't do a very good tilde there. Approximately normal with mean mu and standard deviation sigma. Think about why that determines the curve. Well, mu, if I change mu, right? If I do, so this is mu1. If I have mu2, well, now the curve is going to be peaking at a different spot, right? So changing the mean just slides the curve up and down on the x-axis. What does changing the standard deviation sigma do? I want you to think about it. Try to sketch it out yourself. If I make the standard deviation bigger, what happens to the curve? If I make the standard deviation smaller, what happens to the curve? Think about it. Okay, did you pause me? Now, here's what happens if you make the standard deviation bigger. Same mu, but if the standard deviation is bigger, the inflection point happens later, so it flattens the curve out. Remember, standard deviation is the typical distance from the mean, so it's spreading out the data, it's flattening it out. And if we made the standard deviation smaller, it would squish it all, be skinnier. Okay? So standard deviation smaller, standard deviation bigger. Now what we like to do is what's called the standard normal distribution. So here's what we would do with the standard normal distribution. We make the mean 0 and we make the standard deviation 1. So all the data is centered at 0 and it's the standard deviation, the typical distance from the mean, is exactly 1. In fact, we can transform any normal data. So if it's got some shape that like this shape right here, but its mean is not 0 and its standard deviation is not 1, we can transform it into the standard normal distribution. Now the variable we use for the standard normal distribution is z, and I'll show you that in just a minute, a very important formula. And this actually comes in handy because what we can do is by standardizing, by making everything have the same mean and the same standard deviation, we can compare data because we can see how far away is it from the mean. The idea is how far away is a particular value from the mean in units of standard deviation. So it looks like this. The formula is, and this is a very important formula, very, very, very important, x minus mu divided by sigma. So if you're given some distribution that's approximately normal, so x is approximately normal with mean mu and standard deviation sigma, and you have a little x value, x1, you can find the corresponding z-score. What we do is transform it, and z is approximately normal with standard deviation 0 and, or excuse me, mean 0 and standard deviation 1 with this formula. Every z value will be the x value, its distance from the mean, how far away this particular value is from the mean, divided by the standard deviation. Why is that helpful? So if I tell you I've got two guys that are trying out for a football team, and they both can bench a certain amount. They can both bench, let's say, 250 pounds, right? But one runs slightly faster than the other. You're like, okay, cool. That's a lot. Seems like a lot of weight. I don't know which guy should we let onto the football team. Well, it might be helpful if you knew the mean and the standard deviation for all of the football players on the team, because then you could compare how far they are from the average. And then instead of comparing these two players on their absolute, like, well, that guy lifts more, right? Maybe it ends up being that that guy lifts slightly more, but that guy is much faster. And how you make that slightly more and much faster comparison is with standard normal. If that doesn't make sense yet, don't worry. Hopefully it will after you try some examples yourself. Okay. One more thing about the normal distribution. It's called the empirical rule. So if we have our mu here, remember at the inflection point is plus 1 sigma, minus 1 sigma. So plus 1, minus 1 standard deviation. 68% of all of the observations will be between minus 1 sigma and plus 1 sigma. Now we go out another, minus 2 sigma, plus 2 sigma. From negative 2 to positive 2 will be 95% of all of the observations. And at negative 3 sigma and positive 3 sigma is 99.7%. So what the empirical rule is saying is that most of the data in a normal distribution is clustered around the mean. most of your observations will be within plus or minus 1 standard deviation. Even more, 95% will be within 2 standard deviations. And 99.7%, almost all of your observations will be within 3 standard deviations of the data. Remember, that's not always going to be true for some random distribution, right? This is only true for our normal distribution. Not just the standard, not just the one where mu is 0 and sigma is 1. Any normal distribution. Mu could be anything, sigma can be anything. But if it's this shape, if it's the normal distribution, it will follow the empirical rule. Okay, in the next video, we'll do some examples. I'll see you then.